All right, so I wanted to talk a little bit more about definite integrals in section 6.2. These are actually cut and paste some definitions and information from your textbook. Talked a little bit about it in class yesterday, how the area under a curve relates to the integral. So as long as the function is entirely above the x-axis, so it's always positive, then if you evaluate the integral, it will be equal to the area under the curve. If the function is entirely below the x-axis, so that would be represented here, f of x is less than or equal to 0, then if you wanted the area, it's just the opposite of whatever you get when you do the integral. If part of the area is above and part of the area is below and you want to evaluate the integral, then you can subtract that. So I want to kind of illustrate this idea here. Find the area enclosed between the x-axis and the graph of y equals x squared minus 3 from x equals 1 to x equals 3. So we're going to want to look at the graph of this. I'm going to plot this. So this is just the parent graph raised or lowered 3, counting by ones. So from here, if I go over 1, I go up 1 because it's not stretched or compressed or anything. Over 2, up 4. And if I go over 3, I'm going to go up 9. And so when I draw that in, and I really don't need this side, okay, we're only interested in from 1 to 3. So if I look at that, I want the area between the curve and the x-axis. So the way I can do this, now I can't do shapes because this is a curve. So if I integrate from, notice that this is negative, we actually have to find the 0 for this. So on this one, if I find the 0, so x squared equals 3, so x equals, notice it'd be plus or minus the square root of 3, but I'm only interested in the positive. So I would need to integrate, if I want the area, I'm going to take the area above the curve, so from the square root of 3 to 3 of x squared minus 3 dx, minus, because we're going to subtract the part that's below the curve, so that's going to be from 1 to the square root of 3 of x squared minus 3 dx. Okay, so we could do that way. And if we did that, we would end up with the area that we were trying to find. In class, I talked about another way to do that. You also could just integrate from 1 to 3 of the absolute value of x squared minus 3 dx. So just be aware of that, and then we could deal with doing the antiderivative and plugging in those values like we talked about in class, or if it was a calculator problem, you could fit in this, but I just wanted to illustrate the idea with the areas. Another, a theorem that's in your textbook in this section says the integral of a constant, and I didn't really talk about this as far as a formula, but we did a problem like this. So if the function is a constant and you want to evaluate the integral from a to b of your constant, then it's just the constant times the difference of those of the limits of integration. So for example, applying that formula, my constant is pi over 2. Now remember, in the notes we talked about how this is a dummy variable. I mean, it really doesn't matter, but if I'm using a d theta, then I'm going to be, my antiderivative, if I were to find that, would be pi over 2 times theta. I'll do the problem that way too. But using this formula, this just says that since pi over 2 is the constant, that I'm going to get pi over 2 times, and then you subtract, so I'm going to have -1 minus a -4. So we just get 3 pi over 2. Now, if you did it the other way, where you take the antiderivative and plug in a -1, take the antiderivative and plug in a -4. If you do it that way, you would have pi over 2 times theta. You would plug in a -1 and then a -4. So we'd have pi over 2 times -1 minus pi over 2 times a -4. So we'd get negative pi over 2 plus 4 pi over 2 equals 3 pi over 2. So we get the same answer. So if you think about it, you can do that. Otherwise, you can do the antiderivative and do the way that we talked about in class. So I wanted to do a few more examples. This one, the directions say to use the graph of the integrand and areas to evaluate the integral. So obviously we could do finent on our calculator, but this is saying to use what you know about this. So you might look at this and go, well, I don't really know about this, but I talked a little bit about this. I did one in class, but I know you have one for homework, so let's take a look at this. So if y is 16 minus x squared, if you square both sides, and then I'm going to add the x squared to the other side, notice I get, this is the formula for a circle with a radius of 4. So it's centered at the origin, since it's just an x squared and a y squared, so it is centered here. My radius is 4, so then if I were to go this direction, this direction, this direction, this direction, I could draw in my circle. Well, notice I'm really only interested from -4 to 4. I'm sorry, -4 to 0. And I'm also only interested in the top half because it's just the positive square root. If from this stage right here, if I had square rooted both sides, I would have had a plus or minus. The positive would be the top half of the circle and the negative would be the bottom half of the circle. So I'm actually just looking for this area. So instead of doing, calculus, we know this shape. So what we can do here to evaluate this integral is to find a fourth of the area of the circle. So the area is going to be pi r squared over 4. So then the radius was 4, so we get 16 pi over 4, or just 4 pi. So that means if I evaluate the integral, notice it's always above the x-axis, so it's just going to be 4 pi. So that's how you can use an area to evaluate the integral. So this is number 28 on page 287, and we are asked to use areas to evaluate the integral. So we have to use areas to evaluate this. So here's my function. So f of x equals x. So that's what we would want to graph, which is just the identity line. Okay, so just a quick sketch there. And this time we're evaluating this from a to the square root of 3 times a. And we're told that a is greater than 0, so over here somewhere. Just pick a spot. We're going to call that a. The square root of 3 times a is larger, so I'm going to put that here. So then I want to find the area between those 2 points. So I'm looking for this. Okay? Which, notice, that's a trapezoid, and I need to find the 2 bases, or add the 2 bases. They don't have to be on the bottom. So these are the 2 bases, parallel sides, times the height, and then divide by 2. So if you plug in, to get this height right here, remember my function is f of x equals x. So to get the height here, I would plug in an a. So this is just going to be a. This one over here, I'm plugging in the square root of 3 times a, and so this height is just the square root of 3 times a. And the difference between them, this is going to be the square root of 3a minus a. Notice that a is not underneath the square root. So to get the area, which is going to, because it's above the x-axis entirely, so I know that the area is going to be the same answer as my integral. So I'm going to add the 2 bases, so I get a plus the square root of 3 times a. I'm going to multiply that times the height, which is the square root of 3a minus a. and then divide by 2. And you could do, we could actually simplify this. As a matter of fact, I'm going to go ahead and do that because I'm noticing right here, if I FOIL this in the numerator, I'm going to have the square root of 3a squared. The outside is going to be minus a squared. The inside is going to be plus 3a squared. And then the last is going to be minus root 3a squared all over 2. And then notice that these cancel, and I'm left with 2a squared over 2, which is just a squared. And that's a lot easier, simplified. So that means now this is one that you can't just finite because we had variables in there. But that's how you can use an area model, even if you don't know the values of the limits of integration. So this is number 30 on page 287, and the directions say to express the desired quantity as a definite integral and evaluate the integral using Theorem 2. Well, Theorem 2 refers back to the integral of a constant. So you might look at this, find the output from a pump producing 25 gallons per minute during the first hour of its operation. And you might think, okay, well, where's the function? So I want you to kind of focus on the fact that it's 25 gallons per minute. And this is a rate. This is a rate of change, which means we can kind of consider this as though it's kind of like the derivative. And so we want to find the output. So we want to find the number of gallons. So, that's right. Okay, so if you know the gallons per minute and you want to know the number of gallons, then that means we need to integrate. Okay, because think about if we knew gallons and wanted gallons per minute, we would be doing the derivative if it was the other way around. So we are actually integrating 25, and I need a dummy variable, so I'm just going to call this dx, and we're integrating over the first hour of its operation. However, pay attention to the fact that my rate is in minutes, so I need to have this first hour represented in minutes. So it's going to be from minute 0 to minute 60. So this is what I want to integrate. So because it's a constant, I can use it. I could either do the antiderivatives, but we have that formula we talked about. So let's practice with that. So all I do is take my function and multiply by 60 minus 0. So you're just multiplying 25 times 60. So we get 1,500. And then I don't want to forget the units. So remember we were finding the number of gallons. So this would be gallons. But I do want to make one comment. I probably should have, instead of dx, I'm integrating over time. It would make more sense to do dt for time because we're talking, since we're talking gallons per minute, I'm integrating over time. So I probably should have used a dt. So we'll change that. All right, so another problem, this is number 36 from your textbook, and the directions say to find the area enclosed, well, I guess this is, you can read this here, find the area enclosed between the x-axis and the graph of y equals x squared times e to the negative x from x equals -1 to x equals 3. So we have to find the area. So then that means I kind of want to know if this is always above the x-axis. And you can kind of tell because remember having this e to the negative x, this would be the same as saying y equals x squared over e to the x. So x squared is always positive. E to the x is always positive. So, so we are going to have something that's always positive. So we won't have to worry about, how when we integrate that. But let's take a look at the graph of this with our calculators. So this is what I did. I just graphed the function, and I just graphed the function, and I did zoom 6 to just do a standard viewing window. I want to show you a feature on here in case I'm not sure if you know about it, but there's one, the top one, the Z box, which I kind of like. You can, if you wanted to just kind of zoom in on a region, I'm just using the arrows to get my starting spot. We're going from -1 to 3, so I can kind of use that as my guide. I'm going to push enter, And then you're just going to use the arrows. That just kind of locks it in place. With your own calculator, it's probably easier because you don't have to, you can hold it down. I can't do that on this one. So I need to just at least get past that 3, and I am. Now I'm going to do the down arrow to get kind of below the x-axis to get a good picture, and then hit enter. So then it just kind of zooms in on the region that we're interested in. And notice, just like from -1 to 3, we do see it turns there, but it's still above the x-axis. So we can actually, if we want to find the area, because we know that it's completely above the x-axis, then we can just integrate this from -1 to 3, x squared e to the minus x dx. This is a problem. As a matter of fact, the directions say to use finite to do that. So on your calculator, we can just, if we go alpha, F2, finite is number 4, and we have from -1 to 3, x squared e to the negative x. Oh, wait, what happened? Here, let me hold on here. Okay, so here we get an answer. So we get, whoops. Approximately 1.872 if we round to 3 decimal places. So this next set of problems, and I really had wanted this to just be an activity that you guys did in class. I was just going to get you started. So I'm just going to get you started and then let you kind of think about these. So if you, this problem says in exercises 47 to 56, so they kind of all go together. Use graphs, your knowledge of area, and the fact that from 0 to 1, the integral from 0 to 1 of x cubed dx is equal to 1/4. So what I've graphed here is f of x equals x cubed. So that we have the graph of the integrand. So from 0 to 1, they're telling you that the area is 1/4. So that's this right here. So they're saying that area, or that, because it's above the x-axis, so we get 1/4. So then they say, okay, well, what happens if you go from -1 to 1 of x cubed? Well, notice that means -1 to 1 means you're going from here, from -1 to 1. Remember, the area, it's the area between the x-axis and the function. So we would be, so for number 47, we'd be talking about this region. Well, if this is 1/4, this would be -1/4 because it's below the x-axis. And if we want to evaluate the integral, then we're going to take the part that's above, and then we have to subtract the part that is below. So the well, and we're subtracting the area below. The area above is 1/4, the area below is 1/4, and when you subtract them, you get 0. So, or you can think of it as adding the opposite. So I think of this as a positive 1/4, and this is a negative 1/4. So the net, when you combine that together, is going to be 0. So then on number 48, we're looking at, let me erase parts of this. Actually, I want to keep my function curve. Okay, so if we want now to do number 48, so we're evaluating from 0 to 1, so it's the same limits of integration, but this time it's x cubed plus 3. So imagine if we take our function and we just raise it up 3. So now it's here instead. So what happens, if you think about this, is here's the little piece I started with that was 1/4. And think about what I've added to that. Because remember, we're going from 0 to 1 between the x-axis and our curve. So here's a fourth, but notice I've added a rectangle 3 times 1, so I've added an additional 3. So this one is then going to be 3 1/4, or we could have 13/4. So that's kind of what you're doing. You're thinking about what happens to the graph. So like this one is going to move. Oh, can I have a redo? I don't want to redo this. Let's pretend. Wait, is it on here? No, I did not. Oops, that was a major oops. I did right here. Oh yeah, we did x cubed plus 3. Sorry about that. So that was not 48. I don't want to redo the whole video, so I'm not gonna do that. Actually, it was fine. Little brain lapse. That one actually was fine, because that is what we want to do. It was moved up 3. It's number 49 that this one is going to be moved to the right 2. This one was up 3. That was fine. Parentheses, I guess, threw me off, second guessing myself. So we want to move this one to the right 2. So if you actually moved this way, and then we are looking for, now this time they changed the limits of integration though. So now we're going from 2 to 3. And so so that's kind of what, I'm not going to go on, but that's kind of what you're doing on all of these. So think about the graph. You can use the graph, you can graph it on your calculator, I guess, if you needed to, but just using that idea to come up with those.